Now this time let's try to learn phase diagram module. So in the phase diagram module, we can set up axis and we can do the phase diagram calculation. We can do the very simple binary phase diagram calculation, ternary triangle phase diagram calculation, and then multi-component phase diagram calculation. And the axis, so like x-axis and y-axis, for example, can be changed with many different variables. So we can use, for example, composition. So x-axis as a composition, y-axis as a composition variable, and sometimes we can use the x-axis as the composition, y-axis temperature, and the other way around. And also we can set up x-axis as composition or temperature, and the y-axis as a partial pressure of the oxygen or some other gas species, so activity of some species. So all this kind of calculation is possible in the FACSAGE. Typically, the FACSAGE can handle up to 8 component system. So, I mean, if you think about the most of the material system, you are in interest. Most of them is probably up to about 4 component system, and then if you include some minor element, minor species, you can actually go to the 6 or 7 component system. And typically, if you go to the more than 9 or 10 component system, there's the many small minor element, minor species you can easily neglect, and you can actually downsizing it to the 3 or 4 component or 5 component system. So when you do the phase diagram calculation, you can start with a very simple system and then build up more and more. So you can see actually the effect of those kinds of the impurity species in the phase diagram. Okay, so that's actually one of the general suggestion. So now general suggestion for the phase diagram actually calculation. Otherwise, if you actually dump in all the very complex system from the beginning, then sometimes it's very difficult to understand what's going on. Okay, and so it's the same actually advice for the equilibrium calculation as well. So let's go to the now phase diagram. So here, when you actually look at the FACSAGE main menu, phase diagram module is this one. So when you click this one, you could have this kind of the window. So, and like in the equilibrium module, it always remembers the last system you did the calculation before, and then it will ask you automatically, would you like to load the last system you calculated? And if you say no, then it will just start from the beginning. So yes, so you can have the new actually the phase diagram calculation input like this. So you have to like in the equilibrium program, you can start with unit, for example, so unit, and you can select what kind of unit you want to use. So for example, let's start with the Celsius and the mole, and then ATM and joule is the energy and the pressure, so I don't care that much at this time. Say okay. And then now the database. So I want to use the, for example, CaO SiO2 binary system. Then I want to calculate CaO SiO2. Then FT oxide database is good enough. So I select FT oxide. Okay. And then I'm going to add a 2 component CaO SiO2. So if you look at actually this, the input menu, this is similar to the equilibrium program. The only difference is we don't have the amount of the CaO or amount of SiO2. So we don't have the amount of species assigned at this moment here, because we're going to assign that actually the amount as axis later in the actual calculation, just before the calculation. Okay, so CaO SiO2 is good enough. And then here, many different options, but we're going to look at this kind of option later because this is more advanced option. So for the moment, let's just look at only classical phase diagram. So whatever actually the phase diagram you are typically calculating, they are mostly fall into this actual category, classical phase diagram. Okay, and then to click next. And of course, if you're first time to use FACSAGE, it will be like this. And so you don't see actually what kind of solution page is existing. But if you click this one, show, then you can see the solution page, which is suggested by the FACSAGE, considering the species you enter with your database selection. So the only actual solution in this case is the slag page. So I can click this one, so I can use this one. I use the I option automatically because this is the by default in the FACSAGE. Okay, and then you can choose also slag phase. Similarly, if you click the liquid phase, it again recommends you to don't use the pure liquid phase, because this and this one is basically same, and it may have some conflict due to the very small mistake. So you can just remove it, this one. And then you can now go to setup. So you select the phase. So I know CAU SiO2 binary phase diagram. I select all the possible phase. Now I have to set up what is my y-axis, what is my x-axis. So that's variable here. So you can go and then click the mouse left button here in the on top of this, actually the small, actually the column here, or you can go to variable here and then click the variable, then it will open the same window here. So can I close it? Variable, or you can go here and then click it here, then it will show the same, actually the small pop-up window to actually set up your x-axis and y-axis. So here, now you have the variable, so xy axis diagram or square, reciprocal diagram, triangle diagram. And we have only two components here, CAU, SiO2 we enter. So the only option we can use in this case is xy variable, xy axis, this kind of diagram. And then you can choose the now option here. Would you like to change the composition as a one-off variable? Or would you like to use the activity as a one-off variable? So it means activity of CAO or activity of SiO2, okay? And sometimes you can use the RT lone activity too, okay? So we're going to look at this kind of example later with the partial pressure. And right now we can just use the simply x-axis as a composition, okay? And then click next, then the other side is activated here. And now, more simple one, and we can choose the, for example, x, y constant and etc. So y-axis as a temperature, t as a y-axis, and then you can say from 0 degree to 2000 or 3000 degree, for example, if you like this. And then pressure is constant at the 1 atm. Okay, that's good. And then you can say, okay, SiO2 over CaO SiO2. So 0 CaO, 1 SiO2 over 1 CaO plus 1 SiO2. So SiO2 over CaO plus SiO2. It's a kind of the mole fraction because it's in mole. So this is the mole fraction of SiO2. And at x-axis from 0 to 1, like this. Is okay? And you can use the log, actually the weight percent or log mole fraction or log weight fraction as one of axis if you like to. And this is useful when you do the, for example, in steel making, inclusion phase diagram calculation with log 10 aluminum concentration, log 10 oxygen concentration, something like that. And then you can use the log here, okay? But most of the time, linear scale is also okay. And say okay. Then you can set up the already x, y axis, and then the next thing is you can just use the click calculate. So calculate, then TextAge will automatically start to do the paradigm calculation. Okay, so let's make it a little bit small. So when you have this kind of window here, so when TextAge is to do the thermodynamic calculation, you can have window like this. So here, and by default, you can have this kind of the stable phase, actually the list. So you can see that there's slag phase and CA2SiO4 and all kinds of phases. And this is also, I don't know, it's you can select the option to get this one. So this shows you some little bit cosmetic, actually, the function in the phase in the phase diagram. So if you don't like, you can just unclick it and you can just remove it. I don't need it, this one. And here, so as soon as you actually do the thermodynamic calculation, you can see that if you move the mouse, sometimes you can see this kind of dotted line. All this dotted line is the tie line, okay, in the phase diagram. So, and then also when you look at here, so if you move, then at the composition, at actually the point, the coordinate, what the point is actually the showing, and at that point, you can see what kind of phase is stable. So, can you see Ca2SiO4 plus CaO? Can you see that? So all this area is Ca2SiO4 plus CaO stable area. And then if you do the mouse left click at any composition here, okay, then it will place what is the most stable phase. So each label, either labeled what's the stable phase at that composition area here. Okay, and then here again, you see, and mouse left click, mouse left click, left click. Okay, and then you see all this one. Okay, so let's just label just for fun all this one, and then of course here too, and here too, if you like, here, and then even this one. Okay, and so when you have the phase diagram, you have to read always at the given temperature, because the thermodynamic phase equilibrium is only working at the given temperature. Because that's the zeroth law of thermodynamics. All the phase in the given system in equilibrium condition, the temperature of the each phase should be same. So everything in the system should be in the same temperature and the pressure condition. So so you have to read actually you can change the composition x-axis. However, and when you actually fix the temperature, then you can tell what kind of phase is stable here. So when you have tie line like this, left side of that tie line and then right side of that tie line is the actually equilibrium phase. Okay, tie line is connecting two equilibrium composition at the given from the given composition, two equilibrium phase composition from the given actually the input. So here, this CAO phase and then this liquid phase is stable. So liquid composition is this one, CAO composition is this one, and then from the Levy rule, this divided by this amount of the liquid, this divided by this amount of solid, CAO is existing. Yeah. So do you recall this one in the phase diagram? And now, so the fact sage always show you in all this one. So, and for example, in this case, left side, Ca2SiO4 S3 phase, right side is the slag phase, okay? And then here you can see the Ca2SiO4 S2, S2, and then Ca3Si2O7 phase on the right side, okay? So S3, S2, and S1. So Ca2SiO4 have three phase, three polymorphs. So low temperature, and then intermediate temperature S2, and then higher temperature S3. Okay, all this one have three different crystal structure of Ca2SiO4. That's why we have three different phase here. And SiO2 also have a lot of the different phase. Yeah, SiO2, S1. Typically, we don't say S1 because it's very first one, and then S2, S4, and then S6 in this case. So it's low temperature quartz, high temperature quartz, tridymite, and then this one is the cristobalite. Okay, so you can have all these kind of phase. And then when you go here, this is interesting. If you click this area, you say slag plus slag number 2. So left side is slag number 1, right side is slag number 2. So we have two liquid phase, liquid slag. So this is slag. So this side is slag, and all the way the other side is also slag. So you have single slag on the outside here. Inside here, you have two separate slag phase, two separate liquid phase forming. Okay, and this is so-called the liquid miscibility gap. So two immiscible liquid is existing. That gap, we call it the area which have the two immiscible liquid phase. We say this is miscibility gap, and in this case, liquid miscibility gap. Okay. So in order to calculate this kind of the miscibility gap, we need I option of the slag phase. So do you recall? So when you actually go to the phase diagram here, so in the option here, we say I option, and instead of the plus, it say I. I means possible two-phase miscibility gap. Can you see it in this the explanation here? So here, so it say I possible two-phase miscibility. So that's basically what it means, two-phase miscibility. Okay, immiscibility. So in order to calculate this kind of thing, we have to use the two liquid Gibbs energy. Otherwise, we cannot separate these two compositions. So PackSage automatically enter the I option to give you more accurate thermodynamic calculation like this. Okay, so that's why we are using I option or sometimes J option, which assuming possible two kinds of the miscibility gap. So it's a three phase can be existing in that case. Okay. So we can have all this one, and so this is the by default once you do the fact calculation, phase calculation, by default we have this A. This is, if you go back here, it says stable phase label mode. Okay, so when you click it, you can see actually the phase. And then you can go to this one. This is normal normal addition mode. Okay, normal addition mode. It means now if you double click, you can change the name, you can change the color, and everything is possible. Okay, so color LED, then size 20, for example, bold. So you can change the and then also you can drag and drop. So mouse left click, push the mouse, sorry, click your page name and to the mouse right click and then and push it continuously and then drag it and drop with by releasing your right click. Then the this the the, the coordinate of the actual text can be moved, drag and drop like this way. And then of course if you double click, you can change it also by directly. Okay, so you can make actually your fade diagram more beautiful by double clicking, size change, and etc. Everything is possible. And also one of the interesting feature in the fact stage in the phase diagram mode is like this. So this was stable phase label mode. So you can see only what kind of phases existing, the labeling. And now if you look at this one, if you click this one, bulb kind of thing, so it say that phase equilibrium mode. So basically, this one connecting your phase diagram with equilibrium program. So as you actually notice it, the input style and then all the phase selection is very similar to the equilibrium program. So when you move here, I'm just selecting what's the composition and the final temperature. Okay. And then if I use this information, then that, the composition and temperature will enter into the equilibrium program with all the phase selection you did in the phase diagram mode, and then phase diagram module, and then it will give you the equilibrium calculation result. So for example, when you do it here, so let's go back here. So when I move, can you see it in the bottom here? Sorry. In the bottom here, can you see the coordinate? When I move, the coordinate is changing, yeah? So this is the coordinate of my point right now. So when you go here, for example, okay, this is 0.169 and the y-axis is 2198 Celsius. And then if I do the mouse left click here, then the coordinate is LED. And if you don't like it, you can change it here. So for example, instead of this one, I will say 0.15, and then I only have the 2000 degree. Okay, 2200 degree, and then say okay. Then fact says the phase diagram actually enter this information in equilibrium program with all the phase selection that you did in the phase diagram module, and then perform the equilibrium calculation here. Okay, so here when you enter this composition, this coordinate, then you'll have this amount of the slag, and slag composition is like this, and then this amount of CaO, and CaO activity equal to 1, and the rest of them is all 0. Okay, so it's exactly the same kind of output you see it in the equilibrium program. Okay, so you are learning equilibrium calculation from the actual phase diagram module. Okay, so especially if you want to know what's the amount of each phase, I mean, this is very useful. And then let's go to the another one. So for example, let's take this one. Then if you do the calculation again, it's reading the actual coordinate and say okay. And then second calculation result is shown here. So you can see number one, first calculation result, second and third, and etc. So you can check all this, the phase amount very easily. So sometimes, I mean, binary system is easy, and even ternary system is reasonably easy to understand how much phase, according to the Gibbs, the Libor rule, binary Libor rule or ternary Libor rule, you can more or less estimate, okay, what's the amount of each phase at the given composition from the phase diagram. But when you go to the quaternary system, theoretically, it's very, very difficult to know how much amount of each phase is existing in the quaternary phase diagram, because it is not on the one plane. It is actually section at the certain plane, and then the component is not existing on that actually the plane. then you don't know how far it is from that plane. So it's sometimes very difficult. So sometimes you have 0.0000001 gram amount of the phase is existing at there, but the phase name is certainly say that this phase is existing, but you don't know whether that amount is very small or very big. Okay, so you can easily sometimes you can make a mistake, you know, by assuming that there's a lot of this new phase. Okay, but I mean it's very impurity phase sometimes. So if you are using this kind of bulb option, after you do the phase time calculation, if you are using this kind of bulb, you can check couple of points and see how much the phase is existing, and that will be very helpful for you to figure it out quickly. Okay, whether that actually area or that actually the composition region is the good for your application or not. Okay. So once you do all the phase diagram, and you can also copy paste your experimental point here. And once you do everything, you can go to again, this mode, and then you can go and then save or save it. Then you can keep actually this result for the future application. Okay, save, close it. No. And also, if you like this kind of calculation, you always can save actually the result. So file and then save as. And when you do the save as here, so this is for example CAO SiO2 system, then it is .phas. So phase diagram, the file is saved as phas. So if you have some problem for the phase diagram calculation, and if you know some specific phase diagram calculation, and you can actually do the calculation and save the actually phas page file here, and then you can send it to me, then I can open it and then check the result for you too. Like this. So this is CAO, for example, but phase diagram on your own information. And then you can save the .phas or .fig. .phas, if you do it, you can save the both phase diagram you did the calculation in the last time, and then the actual the phase diagram, actually the condition you actually saved it here. So phase, say okay. And let's go to here and then new, for example, yes, yes, and then let's open that actually the file we just saved it and see how it looks like. So open and the file, I did it, click, and then so even can you see it here? The preview is shown here, the file you actually saved here. So if you double click, say yes, and the last calculation, yes, then it remember the fader you did the calculation. Okay. And if you save this file at certain point, then the last saved form will be just showing up for you. So if you did the labeling and etc., if you did here after that, if you go on here and save as, then you can see that the save as actually the result. So for example, let's say I did this one, this one, this one, this one, and then go back and then I save it. Okay, I saved whatever name it is, and then I close it. Yes, and then let's save it. Okay, whatever. And then if I save it again for this file, then it will overwrite the current one page. Yes. Then if I go back, new, yes, yes. And then if I open it again, this one. Now, can you see that? Save the, okay, loaded the figure you hit the last time. And you see now there's actually the labeling already in the actually phase diagram. So last save the figure format. Figure is saved with the PHAS file. Okay, page file. Okay, so if you want to edit something, you have to go here first, pencil. So it's normal edition mode, and then you can just close it. Yes. And then you don't have to save it twice. So no. Okay. So this is very simple binary phase time calculation. Okay. Now let's go to the ternary system. So let's say new. Yes, yes. So let's try to calculate the CaO Al2O3 SiO2 ternary system. Okay. So now, so you have the three component. Okay, I want to do the triangle diagram. CaO Al2O3 SiO2 triangle diagram. And then the database is still FT oxide. That's okay. And then next, then you have all the possible phases suggested by the phase. So I can take it as it is, take everything as it is, not the liquid phase, because liquid is override, same as this slag phase. So it's part of slag phase, so I don't need it. And then go to the variable now. Click here, variable. And then you can here, I have the triangle diagram. Gives triangle diagram. And then, so when you have triangle diagram, by default, you have the two composition, and then one of the composition is automatically determined. Okay, and next. And you can choose temperature as constant, for example, 1600 degrees Celsius. And the axis, A corner. A corner is this one. A corner, B corner, C corner. So the top corner here, I don't use the SiO2 because this is most simple, most normal, actually, the case, SiO2. And then C corner, I will use the Al2O3, that's good. And then B corner, I will say 1 over the all. So it's a CaO mole fraction into the B corner. So it's a SiO2, CaO, Al2O3, like this. Is it okay? So 1 over all of them, 1 of all of them, 1 of CaO on top of the all of them. And say okay. Sorry. And then to calculate. Then Backstage do the calculation like this for you. Yep. And then once you have done, so you see that here CaO, SiO2, CaO, and then Al2O3 here. Okay. So it's a mole fraction base. And when you go through it, so you have the stable phase mode, labeling mode, slag, and this tie line, slag plus mullite. Can you see? This is mullite zone here, and this is slag. And this is slag plus SiO2, I'm sorry. And this one is the slag plus Ca2SiO4. Can you see it? And then here, monoxide, in this case, CaO plus slag, and then all other phase. Okay? And sometimes you want to also put the, the tie line. Then you can actually enter the tie line too. So how you can enter the tie line? Actually, this is the thing. Actually, you can put the tie line here. So can you see it here? Manipulate and refresh and clear and all kinds of things here. Say tie line, isomer phase diagram, and high, medium, and low density. So I mean, whether you want to have a lot of the tie line and then reasonable amount of tie line or very rough tie line in each area. So one domain, so it means I select the one domain and then asking them to do the tie line calculation. So let's try. So I select this one, okay, and then one domain, and then I select this one again, then it will give the tie line inside of this two-phase region, okay, and medium. And then if I say low density and one domain again, and this area, then it will give the very low density actual tie line. And here, if I want to do it, so high density one domain here, then I'll see much more tie line here. And then if you want to do tie line everywhere, then you can say all domain. Then you don't even have to click it because we know all the possible domains. Say okay. So sometimes you're actually missing something. So for example here, you need a tie line, but it was not happen. So this is good, but sometimes it missed something, then you have to do it by yourself. So go back again, one domain, and you can say here, then recognize it now more easily, and then do the calculation for you. So this is also one of the options. You can do it as a tie line, okay? And this is the tunneling, basically the isomer phase diagram at the 600 degrees Celsius for this one, okay? And this is liquidus line, of course, and then all this, the tie line area is two-phase region, okay? And then triangle is three-phase region. That's good. So let's just close it again. Exit. Yes. No. Okay. So this is the ternary phase diagram. And then there's also some other thing you can do it. You can make a quaternary phase diagram now. So quaternary system, so let's just add one more plus and say MgO. So I want to set the MgO amount as, for example, 10%. and then draw this one, CaO, Al2, SiO2 triangle diagram. Okay, you can see this kind of thing very often. Yeah, and I'm still using the mole, but you can use the gram, then you can have the weight percent. So let's try change it. So unit instead of mole, I have the gram. Okay, so now it's weight fraction. And next, and then I select again all of them, all thing, and then variable. Let's click the variable. Triangle diagram. You can select also rectangular diagram with the completion temperature, whatever you like, and triangle diagram with one of the component is fixed. So next, now 3, and then temperature 600 degrees Celsius. As you can see here, the last one is always by default, the one you want to make it constant. Okay, so first 3 component here is the A, B, C. So you can choose the A, B, C among the first 3, and then the last one, the fourth one, fifth one, sixth one, if you have, all of them should be constant under this triangle diagram. Okay, so that you have to remember. So in order to actually pick the certain composition that actually the species should be not the top 3, not the first 3. It should be fourth or later. Then you can pick that amount as a constant value. Okay. So again, I want to have the SiO2A as SiO2, and then click this one. By clicking up, you can actually change the one. So 1A, and then C corner. C corner is Al2O3. That's good. And then B corner, C. B corner is in this case CaO. B corner is CaO. And then if you click one more, then MgO over entire thing. So MgO over the entire system. Then it means it's MgO. In this case is grams. So it's mass fraction. Okay. So if you want a 10%, 0.1. This is same as 10%. Say okay. And then click. Then not moving. Okay, moving back here. So now it's doing the some calculation for the CaO, Al2O3, SiO2, MgO system with MgO mass fraction, MgO weight percent at 10%. Okay. So you see MgO over this one is 0.1. And you can have this one. Okay, all these phase labels. So you can see what kind of phase is forming. It's now spinel phase is forming here, yeah. And then there's some other phase. Okay, so one thing you have to be also careful in this calculation result is like this. So in the sum phase diagram book, we show that because it's 10% of MgO is taken already. So this coordinate here start from 0 to 0.9. Okay, so to actually show the amount of SiO2, 0 to 0.9. Okay, and then same thing for the Al2O3 or CaO, 0 to 0.9, and same thing Al2O3, 0 to 0.9. So with a 0.1 MgO, then everything is 1. Altogether it become 1. Okay, this is same calculation. However, in this calculation, instead of using 0 to 0.9 scale for the CaO or SiO2 or Al2O3, we denormalize between these 3 to 0 to 100%, 0 to 1 again. So 0 to 1 here, but 1 of SiO2 here means 1 of SiO2 plus 10% additional of MgO. Okay, so you have SiO2 is basically 0.9. So among the 0.9, if you to renormalize that into the 1, this is the coordinate of SiO2. Okay, so when you read this composition, so for example, when you read this composition here, you will say, okay, I have, so SiO2, 0, 10, 20, 30, 40, 50% of SiO2, and then Al2O3, 10%, and then CaO, 0, 10, 20, 30, 40%. However, in reality, this is 0.5 times 0.9 amount of SiO2, and then 0.1 Al2O3 times 0.9 amount of Al2O3, and CaO 0.4 times 0.9 of the CaO. Okay, because altogether should be 90% because we took the MgO as 10%. Okay, so this is the normalized phase diagram among the remaining species. Okay, remaining actually the component. And so, for example, you can easily see this one when you click this phase equilibrium mode. Let's go to here. I mean, as I show you this one at this point. If I do the calculation, so turn it triangle diagram, SiO2 0.5, for example, Al2O3 0.1, then it's exactly the point I was talking about. And then if you do the calculation, you see it's 1 gram of the slag. MgO is 10%. And SiO2 was 0.5 times 0.9. So 50% times 90%. So it's 45%. Okay, and the rest of them is same. So you have to be little bit careful how to read the coordinate here. So you do the very good calculation, but after that, when you plot your data point into this diagram, you have to renormalize. You have to normalize between the CaO, Al2, SiO2, and then place them inside here. Okay, it's just slightly complex, but if you understand this one, it's okay. Okay, so that's the one of thing you have to be very careful. And then when you do the quinary phase diagram with the two components fixed, you can do the similar thing. You can add like MgO, you can add like MnO, so MgO, MnO in the last two, and then you can fix them, and then you can use the three corner, first three actual component as A corner, B corner, and C corner, and then make this kind of triangle diagram. Okay, that's good. So this is very simple, basic actually the function of the phase diagram. So the phase diagram is very, very easy to use. And because you have learned all kinds of technique already in the Equilib program, and you are just simply clicking and then plot it, then the only thing you have to know is how to read those kinds of phase diagram information later. Okay. So in the next session, I will show you a little bit more complex case for the phase diagram. Okay. Thank you very much.